Hello, today I want to talk about the Chebyshev bounds. The Chebyshev bounds give an upper bound of the probability of a set based on known expected values of certain functions. The simplest example is Markov inequality. If x is a random variable on R plus with ex equals mu mu, then we have the probability of x greater or equal than 1 is smaller or equal than mu, no matter what the distribution of x is. Another simple example is Chebyshev bounds. If x is a random variable on R with ex equals mu, and ex minus mu square is equal to sigma square, then we have probability of x minus mu is greater or equal than 1. The probability is smaller or equal than sigma square. Again, no matter what the distribution of x is. The idea behind these simple bounds can be generalized to a setting in which convex optimization is used to compute a bound on the probability. Let x be a random variable on S belongs to Rm, and C belongs to S be the set for which we want the bound. The probability of x belongs to C is. Let LC donates the 0 to 1 indicator function of the set C, and LCZ equals 0 if Z is not belongs to C. Our prior knowledge of the distribution consists of the known expected values of the functions is EFIX equals to AI. I is from 1 to n, where Fi is the Rm to R. We take F0 to be the constant function with value 1, for which we always have EF0x equals A0 equals 1. Consider a linear combination of the function fi given by fz is equal to sigma I from 0 to n xi fiz. From our knowledge of EFIX, we have EFX equals A transpose X. Now, suppose that f satisfies the function fz is greater or equal than LCZ for all z belongs to S. For example, f is pointwise greater than or equal to the indicator function of C on S. Then we have EFX equals to A transpose X greater or equal than ELCX equals probability of X belongs to C. In other words, A transpose X is an upper bound on probability of X belongs to C, valid for all distributions supported on S with EFIX equals AI. We can search for the best such upper bound on probability of X belongs to C by solving the problem of this. Minimize x0 plus a1x1 plus dot 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 plus anxn subject to the following inequalities. With variable x belongs to Rn plus 1. This problem is always convex, since the constraints can be expressed as g1x equals 1 minus inf fx is greater or is smaller or equal than 0. g2x equals minus inf fx is smaller or equal than 0. g1 and g2 are all convex. The problem can also be thought of as a semi-infinite linear program. For example, an optimization problem with a linear objective and an infinite number of linear inequalities, one for each z belongs to S. In simple cases, we can solve the problem analytically. As an example, we take S equals R plus, C equals 1 from 1 to infinite, F0x equals to 1, and F1z equals to z, with EF1x equals to EX equals to mu, which is smaller or equal than 1, as our prior information. The constraints Fz is greater or equal than 0 for z belongs to S reduces to x0 is greater or equal than 0. x1 is greater or equal than 0. The constraints Fz is greater or equal than 1 for z belongs to C. For example, x1 and x0 plus x1z is greater or equal than 1 for all z which is greater or equal than 1. Reduces to x0 plus x1 is greater or equal than 1. The problem is then be the minimize of x0 plus mu x1 subjected to x0 is greater or equal than 0 and x1 is greater or equal than 0 and x0 and x plus x1 is greater or equal than 1. Since 0 is mu is greater or equal than 0 and smaller or equal than 1, the optimal point for this simple linear problem is x0 equals to 0 and x1 is equal to 1. This gives the classical Markov bound, which is the probability of x is greater or equal than 1 is smaller or equal than mu. In other cases, we can solve the problem using convex optimization. The Chebyshev bound problem determines a bound on the probability of x belongs to C for all probability measures that satisfy the given expected value constraints. Thus, we can think of the Chebyshev bound problem as producing a bound on the optimal value of the infinite dimensional problem. Maximize the pi dz subjects to initial Fiz pi dz is equal to ai. I is equal to from 1 to n. And pi is greater or equal to 0, where the variable is the measure pi, and pi is greater or equal to 0, means that the measure is non-negative. Since Chebyshev problem produced a bound on the problem, it should not be a surprise that they are related by duality. While semi-infinite and the infinite dimensional problem are beyond the scope of this book, we can still formally construct a dual of the problem, introducing a Lagrange multiplier function with Pz, the Lagrange multiplier associated with the inequality Fz is greater or equal than 1 for z belongs to C, or Fz is greater or equal than 0 for z belongs to Sc. Using an integral over z where we would have a sum in the finite dimensional case, we arrive at the formal dual maximum the Pz dz subject to the Fiz Pz dz is equal to ai. I is from 1 to n, and Pz dz is equal to 1, and Pz is greater or equal than 0 for all z belongs to S, where the optimization variable is the function p. This is essentially the same as the problem above. That's all. Thank you.